All right. Hello, everyone. Happy Monday. Welcome to week 6. Uh, we are getting precious close to the end of the semester. Um, uh, Course logistics things to talk about. There is a new problem set posted, problem set 5. It is due this Friday, July 19th. So make sure you're taking a look at that. The late due date for problem set 4 is 2 days from now, so Wednesday the 17th. Um, so if you haven't submitted that already, make sure to do that. Um, Programming assignment 2 is due today, and then the late due date is the 20th, which is Saturday, I guess. Um, so a lot of things due. Uh, Make sure you stay up to date with that. I will be releasing the PDF for the third programming assignment sometime today. It is mostly ready. We just have to make sure that the auto grader works and is in particular possible to make work. But once I have confirmation on that, I will release the PDF and you'll have 2 weeks to work on the third and final programming assignment. Um, Also, just a reminder, just like for PA1, there's a optional 10% write-up for PA2. So if you want the chance to get up to 10% extra credit, submit a write-up. Um, there's there should be some guidelines as to like what to write about if you don't know. But in general, you can just kind of tell me cool stuff that you did. Tell me, um, yeah, just like reflect on the project, I guess. I don't know. Um, so yeah, extra credit there. The final exam is, according to my Purdue, posted to be at 8 a.m. on Friday, the last day of class. I, number one, don't want to show up at 8 a.m. And number two, don't want to uh, deal with like all the different time zones and like managing so many different exams to proctor. So I think I'm going to make this a take-home exam, unless anyone objects to that. Uh, so I'll release it on like, I guess I'll release it on Friday, and then you'll have like until the end of the weekend or something like that to turn it in. Or maybe I'll have to do it earlier. I don't know if I'm allowed to have things. Well, yeah, okay. It'll be a take-home exam. You'll have a few days to finish it. I'll either release it Friday and have it due Sunday, or I'll release it on like Wednesday or something and have it due Friday. Um, yeah. So if you were concerned about uh, exam times, don't be, I guess. Cool. Um, exam the midterm exam grading is underway. Hopefully, we should have grades out for you by the end of the week. Uh, and that also applies for the problem sets, which I know are we're a bit behind on grading. Um, so yeah, hopefully all those grades will be coming out in the next few days. Um, any questions on like logistical stuff before we move on to content? All right, let's do content then. Um, uh, Zoom like updated. It's weird. I don't like it. There's- I'm just gonna make a new whiteboard. All right, here's my. Here we go. Perfect. Okay. I assume everyone can see the whiteboard. So, today I want to finish up talking about hashing, and then I want to get into the next topic, which is probably going to take us through the end of the semester, which is graphs. Um, so let's finish up hashing first. So, as a quick refresher from Thursday and Friday, because I guess there's been a weekend in between those lectures and now, um, the idea is we want a data structure called a hash table, which supports constant time, lookup, and insertion, right? Um, and uh, the trick, the way we go about doing this is maybe I want to say pre-allocate space for m objects. Um, maybe to insert compute the index for an object and write it to that index, right? Right, so this is something like t index h of k equals k, right? We look up, we only need to check that index, right? So we can return t at h of k, right? And then, of course, h is going to be surjective, but probably not injective. So we need to resolve collisions. And this is what we talked about on Friday. So one method for resolving collisions oh, I misspelled collisions, was chaining, right? So this is each plot is a linked list. When we insert into the list. When we look up, we traverse the list, right? Um, and here we can also delete, which is just deleting from a list. Um, and as I think we discussed, if you make this a doubly linked list, then insertion, lookup, and delete are all on average constant time operations, right? Because the fact that you have to traverse a list to look up, or the fact that you have to traverse a list, or insert, you can just insert at the head, so that's constant time. Delete, you can delete in constant time because you just have to like move the next and the previous over, right? And then the fact that you have to traverse a list for lookup is kind of squashed by the fact that the lists are going to be much, much smaller compared to the size of the table. So we calculated this. This depends on the load factor, alpha, right? Which is n over m, where n is the number of elements in the table, and m is the size, right? So we saw that it depends on alpha, and we saw that if you make n, or it like lookup is something like big O 1 plus alpha. And if you make m big enough compared to n such that alpha is a constant, then this whole thing is going to be constant time, right? So this is the chaining method for resolving collisions. Again, this is all review. I'm just kind of going over it. The nice thing about chaining is our table can get as big as it wants. Alpha can get as big as it wants to. So maybe I'll say pros can extend indefinitely. Indefinitely. And then the cons, this is very memory inefficient. Right? Because we need space, we need to allocate space for the table. Each cell in the table is going to be a pointer. In addition to that, every like element in the table is going to be a linked list node, or every like element, every object that we've inserted into the table is going to be a linked list node plus an additional pointer. So we're going to have like 2n plus m pointers and n objects worth of memory, right? This is a lot of memory to use. Also, the fact that we have to like traversing a linked list can be really bad because every time we dereference a pointer, these are all like in different places on the heap. We get a bunch of cache misses. We get a bunch of things that our compiler can't optimize away. Pointers are just generally very annoying, right? So, right, it's simple to think about. It's simple to draw a picture of. It's you can sort of keep inserting and deleting. You don't have to worry about things, but it is very memory inefficient. And just generally inefficient. So the other thing we talked about instead was open addressing. And I can't remember to what extent I covered open addressing. I think we had just gotten to it. So maybe I'll start at the beginning of that, right? The idea of open addressing is slot in the table directly holds an object. So in particular, this means no pointers. Resolve collisions by moving somewhere else in the table. Right? So our hash function, instead of being something like h of k, this now becomes something like h of k, comma I, where h of k comma 0 is the original hash. And we have another k comma 1 all the way to h of k comma n, right? And so we start by trying to insert something at h of k comma 0. If it collides, if there's already something there, then we increment I, we move on to k comma 1, move on until we hit here. If we get to h of k comma m and we've had collisions all along the way, then we know that the table must be full, right? And so in particular, for this to be correct, this requires that h of k, if you think of this as just a function from 0 to m to 0 to m, this should be a permutation. Right? In particular, this should be surjective. So like whatever hash function we visit or whatever hash function we use should at some point visit every possible slot, right? It's just the key determines the order in which it visits the slot. Or maybe somehow the hash of the key determines the order in which it visits the slots. So conceptually, this is the idea of open addressing. Now, this sequence, right? Or maybe I want to write it like the sequence of slots that you get. This is called the probe sequence. Right? Because the idea is we start by probing the table at this position, and if that doesn't work, then we probe the table somewhere else, and we just kind of keep going and probing the table at different spots until we either find something that's empty or we realize that the table is full. And so a lot of the stuff to talk about for open addressing goes into like determining this probe sequence, right? Or like how do we define um, a function like this, right? What does the dependence on I look like? So maybe I'll pause for questions here. Conceptually, does this make sense before I talk about specific probe sequences or specific strategies for doing that? All right, I see a yes. Is that a yes that makes sense, or yes, you have a question? Yes, that makes sense. Perfect. Okay. All right, if there's no other questions, let's look at probe sequences. Right. So the first one is linear probing. Um, the idea here is, oh, by the way, I guess I should mention the book, the CLRS book. I realized I have the third edition. If you go online and you look for a PDF, the first link gives you the fourth edition. I personally have beef with the people who wrote the fourth edition because they cut out some of the best stuff and replaced it with things that are not as interesting, in my opinion. In particular, the fourth edition does not talk about uh, probing. It doesn't talk about like it mentions linear probing. It doesn't talk about quadratic probing. It really just talks about double hashing, and then it just gets rid of a bunch of other really cool stuff. Um, so fourth edition bad, third edition good. I mean, use whatever edition you want, but I guess the point is, if you want to read more about what we're talking about in class, um, this is going to be in chapter 11 of the third edition. It's not going to be in the fourth edition. Um, So if you were looking at that PDF and you couldn't find reference to what we were talking about, that's why. Uh, okay. So linear probing, we have a hash table. I'm going to draw some slots in here. The easiest thing we could do, oh, yeah. the easiest thing we could do, let's say we've written some K1 into here, right? And we try to hash K2, and it takes us there, right? Easiest thing we can do is just move on to the next one, right? So put K2 there instead. And then if we get K3 and K3 wants to go in one of these two slots, just move it on to the next one, right? So if we've got a bunch of keys that all hash the same slot, we'll just sort of keep traversing forward until we find something empty, right? So here, h of k, so I mean, we have some sort of like auxiliary hash function, like h, we'll call it h prime, right? So we'll define h of k equals h prime of k plus I, and then of course mod by m, right? In general, we can put whatever coefficient we want in front of the I. So we could say something like h of k equals h prime of k plus maybe c times I mod m. So this is going to be linear probing with a step size of c. In some places, you might see linear probing used to only refer to this one, where c equals 1. But in general, just know that you can kind of anything that sort of like moves linearly along the thing is a linear probe, right? Okay, so the trouble with linear probing is the probe sequence is entirely determined by any one element in the probe sequence, right? So um, if, well, okay, okay, yeah. What I want to say is here, right? We ask that the probe sequence is some kind of permutation of the indices from 0 to n, right? Maybe 0 to m minus 1. Maybe I want to make this open, right? Um, so we ask that it's a permutation. Now, intuitively, we probably want like hash tables work best when the keys are as uniformly distributed as possible, because that means that our load factor is a very good approximation for like how many steps we're going to take anywhere. Or that means that like we get very close to the average case complexity, right? And so you might consider the fact that you want this permutation to be equally likely to be any like you want every possible permutation to be equally likely, right? So in an ideal uh like uniform hash function, um maybe I'll write this here. Every possible probe sequence with equal probability, right? If one probe sequence is a lot more common than all of the others, or like for example, if we always pick the same probe sequence, then you can imagine keys will sort of like build up along those along the terms in that sequence and sort of nowhere else, right? Or they'll sort of build up like towards the beginning of that probe sequence. And so we won't have keys distributed uniformly throughout our hash table, and that's bad, right? Now in practice, um, this is not possible, right? Because how many probe sequences are there? You can shout this out in the chat. n factorial question mark. That's a fun way to write it. Yeah, m actually, because m is the size of the table, right? So there are m factorial total sequences. I guess factorial question mark is not the same as an interrobang. Uh, but yeah, there's m factorial total sequences, right? So let's keep this in mind and then move on to the linear probing. Yeah, n factorial. If we look at linear probing, how many possible sequences can this produce? Or maybe how many unique probe sequences are possible? You can shout this out in the chat. Any thoughts? If m is divisible by c, then c. Oh, yeah. So the divisibility thing is a good point. I think I mentioned this last time, but we need uh if if c divides m, right? Then let's say something like m equals 6 and c equals 2, right? This is actually very bad because what's going to happen is let's say h prime of k is 0, right? So we're going to visit 0, then we're going to visit 2, then we're going to visit 4, then we're going to visit 6, which is 0 again, and then 2, and then 4, and so on. And this probe sequence is never going to hit 1 or 3 or 5, right? So we need it to be the case that that C and M are relatively prime, right? So for example, M equals 6, D equals, oh, 6 is actually a really bad idea for this, right? Uh, 1 or 5, yeah, C equals 5 or C equals 1. That way, it goes 0, then 5, then 4, then 3, then 2, then 1, then 0, and so on, right? And so now this one visits every element in the table. Whereas for this one, even if we had space in slots 1, 3, and 5, this probe sequence would erroneously report that the table is full, right? And so we wouldn't get the correct semantics. Um, so we do need the order of C inside M to be maximal. Um, each C such that the greatest common factor of C and M is 1 makes one unique sequence. Uh, that's correct. How many such Cs are there? This is P of M, right? It turns out to be roughly linear, right? Um, so on that note, a good way of sort of choosing parameters here is maybe I'll say this is like a heuristic. Uh, let M be a power of 2, be odd, right? Or let M prime be anything except M, right? That way, you know, like allergies. Um, if n is all twos and c is odd, then there's not going to be any overlap. If n is prime, then it's not going to have any overlap with anything. And so these are sort of good ways to ensure that your probe sequence visits everything. But yeah, there's going to be something roughly there's going to be like roughly a linear number of probe sequences, right? At most. Um, so we get m out of m factorial, which is pretty bad, right? Also, if you consider the case where c equals 1 for simplicity, right? If I put k1 here, k2 here, k3 here, right? Uniform hashing says that every key is equally likely to go anywhere, right? Um, but if I look at inserting some new K4, right? What are the probabilities? Like the only places it can go are here and here, right? So ideally we want it to be 50-50, right? But what are the actual probabilities here? Like what's the probability that K4 ends up going here? Anyone? Yeah, what's the probability that K4 goes here? Right. So we've got two possibilities for like we could say h of K4 equals 0 or h of K4 equals 4, right? So ideally we want the probabilities here to be 1/2 and 1/2, right? But in reality, if we assume that the function we're starting with is nice and uniform, right? So before resolving collisions, K4 is equally likely to hash to any one of these slots, right? So that's 1/5. That's like a 20% chance for each of these, right? If if it if it hashes to 0, it's going to stay at 0, right? If it hashes to 1, it's going to skip to 2 and then skip to 3 and then skip to 4 and then end up at 4. If it hashes at 2, it's going to skip to 3 and then end up at 4. If it hashes to 3, it's going to skip to 4 and end up at 4. And if it hashes to 4, it's going to stay at 4, right? There's 4 possible ways that K4 ends up here, and only one way it ends up here, right? So it turns out that the probability that the hash of K4 is 0 is 20%, and the probability that the hash of K4 is 4 is 80%, right? And this is true assuming nothing about what the new key is, nothing about what the original keys are, nothing about what our hash function gives us, except for the fact that the hash function we started with was already really good in the sense that it was already very uniform, right? So linear probing suffers from this sort of problem, right? And I showed you this for the case where c equals 1, but you can sort of show that like um, for any value of c, things are going to build up at like anytime you have a run of slots filled up with a gap of c between them, um, they're going to sort of the probability of a new key ending up somewhere is going to accumulate to be at the next element in that sequence, right? And so it's the sequence is sort of going to like want to keep getting longer and longer, which is really bad because it means that to search for any key in that sequence, you have to search through the entire sequence, right? I'm being sort of hand wavy here, but your problem set forces you to kind of go into this in a bit more detail. So does that make sense? Any questions? All right, let's move on. So the second method we can talk about is quadratic probing. Right. Quadratic probing comes about when we recognize that the problem with linear probing is the entire sequence is determined by any element in the sequence, right? So in particular, this means that if we build up, like, we get a chain of like K1, K2, K3 building up like this, right? Obviously, if we're inserting a K4, if it collides with K1, then it has to follow this chain and it has to end up here, right? But, or I guess it doesn't have to. But if it collides with, like, if K4 collides with K1, it's going to end up here, right? But if K4 collides with K2, it's also going to end up here. And if K4 collides with K3, it's also going to end up here, right? This is that like accumulating thing that we talked about earlier, right? Because the entire sequence is completely determined by any one element in that sequence, right? Because everything is just going to be a fixed offset from that element, right? We don't want that to be the case. So with quadratic probing, we get this nice property that if K4 collides with K1, it's still going to end up at the end of the chain. But if it collides with K2, it might end up somewhere else. It might form its own chain, right? If it collides with K3, it might form its own chain, which is a lot nicer. So specifically, we start with some nice uniform hash function, right? Quadratic probing says that h of k comma I equals h prime of k plus, I'm going to say c1 times I plus c2 times I squared mod m. Okay, so now instead of moving forward by a fixed step size every time, we increase our step size as we go on, right? So in particular, that means that right, if we've got a chain K1 to K2 to K3, right? If I collide with K1, then the next step I take is going to collide with K2, and the next step I take is going to collide with K3, and so then the next step is going to put me at K4. But if I start at K2, if the thing I collided with was K2 instead of K1, then the step I take is going to be smaller than the step from K2 to K3, right? Because the step sizes here are increasing. Maybe it's better if I draw it like that, right? So K1 to K2 to K3, maybe we can keep going, K4, right? So if I collide with K2, the step I'm going to try to take is going to put me there instead of having me collide with K3, right? So like the next key I insert isn't necessarily going to end up at the end of the chain. Of course, if I collided with K1, then my step sizes are going to match the step sizes of this chain, right? And so I'm not going to have any other choice but to end up out here. But now there's a one in like the chance that I end up at the end of this chain, or the chance that I end up, or the probability that I end up at the next element in this chain is now 2 out of m instead of it no longer depends on the length of the chain, right? The only way to end up here is, well, not necessarily. There's less of a chance that a long chain keeps growing, right? The probability of being added to the end of the chain is much smaller. The only way for it to happen is to collide with K1. So that's quadratic probing. We could look at an example, I guess. I don't know. Does an example feel useful? I mean, it's essentially it's linear, except now you have this extra C2 term, right? So you define your hash function based on this auxiliary hash function and then these two constants, and you sort of just pick constants. And you pick them um, such that every step size or such that every like thing is a proper permutation of Z mod M. Right. So another easy thing to do is C1 and C2 are odd. M is a power of 2. That way, if these two are odd, then well, or maybe just one of these is odd, right? If C1 is odd. Then you're more likely to get a proper permutation. Of course, it depends on the initial key. But you don't have to worry about like only stepping through a subset of the thing anymore. Maybe I'll omit the example for now because we are running short on time and your problem set has you do an example. But we'll notice that so the last one I want to talk about is double hashing. So we'll notice that the problem, like quadratic probing still runs into this problem, right? If h of k1 equals h of k2, they are guaranteed to end up on the same chain, right? And to some extent, even separate chaining has this problem, kind of by definition, because if two things hash to the same thing, then they get inserted into the same linked list, right? So if we're in a situation where like it's not uncommon for our hash function to have collisions, like if a lot of the keys that we care about might end up hashing to similar things, and we want to have to like we want to deal with collisions pretty often. Even quadratic probing isn't going to be very good because we're still going to get these like long chains built up, right? The idea of double hashing is our step size, right? So linear probing said the step size is fixed. Quadratic probing said the step size increases every time you take a step. Here, double hashing is going to say our step size depends on the key, right? So for this, we need two auxiliary hash functions. H1 of k and H2 of k. And then we define h of k comma I equals H1 of k plus I times H2 of k, right? So this looks very close to linear probing, except for H2, like the key determines the step size, right? So even if two keys hash to the same thing, they're going to have a collision on the first step, but K1 is going to take a step of one size, K2 is going to take a step of a potentially different size, right? The only way for this to be a problem is the only way to get like a very long chain built up is if you find a key where H1 and H2 both collide, right? So maybe, for example, right? I'll have like K1, K2, K3, something like that. I try to insert K4. It collides with K1, but that doesn't mean that it's going to like the step size that we get for K4 might be something completely different. So K4 might end up here, and it might not end up at the end of this chain at all, right? The only way for this like really long chain to build up is if we find K1 and K2 such that H1 of K1 equals H1 of K2 and H2 of K1 equals H2 of K2, right? So if both hash functions collide on the same pair of keys, which is much less common. In fact, we can pick H1 and H2 to make that as uncommon as we want, right? So the book provides some guidance, but one thing that happens to work pretty well is H1 of K equals K mod M. H2 of K equals K plus 1 mod M minus 1. Right? This way, for these two to be equal, I don't know. I'm not a number theorist. I don't know what the probability here is, but it seems very unlikely, right? Especially if M is like a nice prime number, then you're going to break all of these patterns, right? So that's double hashing. And your problem set is going to ask you to investigate. Your problem set is, among other things, going to ask you to investigate like patterns where linear probing doesn't work really well, and how quadratic probing performs, and how double hashing performs. So you'll work out plenty of examples there. Does that all make sense? Are there any questions about any of the hashing stuff that we've talked about before I move on to graph theory in the last 10 minutes of class? Now's the time to ask. All right, if there's no questions, I am going to close this whiteboard and create a new one. Okay. So graphs, right? Like I said, graphs are going to be what we talk about for the majority of the rest of the semester. We're going to kind of do a tour through a variety of different graph algorithms. We're going to talk about like topological sorting, depth first and breadth first search in the context of graphs. We're going to spend quite a bit of time on graph search, like shortest path algorithms. We'll talk about spanning trees. We'll talk about maximal and minimal flow. Hopefully all of these or a subset of these words will make sense to you in the next week or so. And then that's, yeah, so this is sort of going to be the last like core course content that's going to be covered. If there's time after graphs, I do want to talk about other fun stuff like amortized analysis and like union find algorithms and stuff like that. But that's that may or may not happen depending on timelines. Okay, so in the last 10 minutes, I maybe want to give some like definitions and like a quick overview, and then we can kind of go into more detail on starting tomorrow. Oh, wait, I meant to release an attendance poll. So before I do that, attendance poll. Wait, let me go back to this whiteboard. Here we go. Wait. open. There we go. Okay. Almost forgot. Would have been tragic. Okay. Attendance poll. Show how uh maybe I'll say of linear, quadratic, and double hash probing, which can be seen as special cases of each other. That's the poll question. I'll leave that up for a moment. And I'll make the thing in bright space. Oop, there we go. All right, that's been up for long enough. Let's switch back to graphs. There we go. For some reason, it wants me to click it twice. Here we go. Okay. So vibes, a graph is a bunch of nodes like this, connected by edges. Okay. Uh, so maybe we can be more formal now. A graph G. I'll use a capital G to refer to a graph usually. I might say like H for a subgraph or something like that. But a graph G consists of a set V of, we'll call these vertices. You'll also hear these referred to as nodes. I like vertices. A set E of edges, right? You might call these arcs. And then pair of functions S comma T from E to V, right? So S takes an edge and outputs the source vertex. T takes an edge and outputs the target vertex, right? So, for example, if I draw the following graph, so I've got 1, 2, 3 vertices. Maybe I've got an edge like this, an edge like this, and an edge like this, right? So maybe I'll call these edges A, B, and C. So we've got V is the set 1, 2, 3. E is the set A, B, C. Source takes A to 1, B to 2, C to 1. And then target is the function that takes A to 2, B, B to 3, and C to 3, right? So these two sets and these two functions define the data of this graph, right? That's a sort of formal, like mathematical definition. We will often draw graphs. We'll sort of leave the edge labels off, and give like vertex labels and like circle the vertices and draw edges like that. Strictly speaking, this is something called a multigraph, right? So this is the most general. Um, this is the most general class of graphs. Um, we can refine this with more adjectives, right? So a simple graph has the property that between any two vertices, there is at most one edge, right? Uh, this is a directed graph because you see that the edges have direction, right? Like the source and the target aren't necessarily uh, uh, like symmetric, right? But we have the concept of an undirected graph, which basically says for every u arrow v, there is a v arrow u, right? So every, for example, this is now an undirected graph. And for the sake of simplicity, often when a graph is undirected and we know that it's undirected, we'll omit the arrows, right? So we could redraw this as just 1, 2, 3, and then just undirected lines, right? With the understanding that this line represents an arrow going in this direction and in this direction, right? Um, so simple, undirected. Uh, maybe we can come back to this on Tuesday because it's 9:42. But that's all I got. If there's any questions, I can stick around and answer them. Otherwise, you are all free to go. Are there any questions?